All right. Well, welcome everybody. Good morning. We're starting our second day, and it's a great pleasure to introduce Maxim Kontsevich, who is the reason for this meeting. The only, I don't have stories to tell. The only thing I was thinking about is that we've been doing this. We met 10 years ago for Maxim's 50th birthday. And it was a great conference, and we're meeting twice this time for his 60th birthday.
Next time, more.
We could do a geometric regression for sure, but I was thinking that maybe we should start meeting every 5 years because clearly, still that's accumulating. We can't really go over and internalize in just one meeting every 10 years. So be prepared. Okay, thank you.
Thank you, yeah. Also know Maxim for many years, but it's still so I will talk about non-perturbative deformation quantization. Yesterday, co-founder Sanders kind of introduced some kind of background with some very interesting formulas, which will be very important to compare with what I explained. We have no interesting formulas. Okay, it will be just words. Okay, I'll remind you of formality theorem from middle 90s. So you consider some just consider coordinate space in arbitrary dimension with our complex numbers, and on this space we have two sheaves of differential graded algebra. One is polyvector fields, another is polydifferential operators. So both sheaves are graded degree -1 as the algebras -1, 0, 1 to infinity. And so for polyvector fields, this have 0 differential, it's called in bracket, and for polydifferential operators, you consider polylinear maps from algebroid functions to itself, given by products of some derivatives. You consider the part of cohomological function complexes abstract algebroid functions, so it gives you a guess kind of bracket and function differentials. Why polydifferential operators? Because here you can do make it sticks local, you can sheafify it. And in principle, I'm not really having this notion of differential operators because you consider differential operators have some order, and we do specify the order. In real life, that can get a good control of order, but I cannot really make a sheaf of operators of some kind of bounded order, whatever, to see what is going on. And in fact, there is a notion of micro-differential operators, so like infinite expression of derivative, which still works on differential functions, and this is the optimal notion here. Okay, but in real life, we have differential operators, and formulas are explicit, some sort of graphs, and the invariant covariant respect to a group of affine transformation. And so it's formally written in affine when you have affine structure. But if you don't have affine structure, you can do something. This interaction, this change of coordinates of this quasi-isomorphism, and then you can put it on any complex manifold without affine structure, and space of choice will be constructible. So, and then the thing generalized to infinity, infinity algebraic case. So that's you can use it just as a black box. And you notice that in degree -1, you get the same component of both algebras, it's sheaf of functions, but they start to differ. So this formality, quasi-isomorphism, it's not unique. There are infinite dimensional space of some such quasi-isomorphisms, and this space of choices is torsor over pronipotent technical group. And we know the structure is it's actually 3 you consider for important group whose Lie algebra is really algebra with generators to degree 3, 5, 7, and to infinity. Yeah. So there are two kind of distinguished quasi-isomorphisms. I don't know what when I will conjecture which one to choose. The original formula used some real propagators. So if you do over real, replace complex numbers by real numbers, it will be still works. And another choice is kind of mathematic. It's compatible with action of mathematic Galois group. It gives you, even in real case, give complex numbers for the quasi-isomorphism. Theoretically, there is a quasi-isomorphism of rational numbers, but it's there's no good choices. Yeah, it's kind of from the existence result. Okay. Yeah, so if you have any sheaf of Lie algebra or any manifold, DG algebra, then you get simplicial set of like formal paths and Markov stack from Markov stacks. You can it's a formal path in essential Markov equation and go up to equivalence, gauge equivalence, and this equivalence between equivalence and so on. But if you truncate, for example, my sheaf of polydifferential operators, this start to be homological degree least one. So it means that here, I don't think this pointer, no. You start with B differential operators and 3 differential operators. But first, you throw away first 2 terms. When considers solutions of the small pattern equations, it will be just what's called star product on sheaf of function series in hbar with various functions. Namely, you can see sequences, infinite sequences of B differential by differential operators, or global by differential operators in a manifold, and I want to make a product F star G, which is usual product plus a infinite series of corrections. And the conditions Markov equation would say that it's associative product. Yeah, if you truncate a little bit earlier in degree 0, then you get not a set but groupoid. And groupoid consists of form. It will be sheaves of algebras, linear over Lorentz series in hbar, which are locally isomorphic to star products. So you can trivialize this on a small open Stein domain. It will be star products, but on intersection of Stein domain, you get you identify the star product by linear automorphism of this space of functions, not algebra, which is deformation of the identity automorphism. So you make any functional series in hbar, f plus however, so it's the hbar squared. Infinite series of differential operators in this formal group. And again, just I want to say this something which is deeply unsatisfactory here with controlling degrees. In real life, this B1 will be operators of order 1 in F and G. B2 will be operator of order 2 in F and G, and so on. And when we make so that's what one can do if one make some product coming from formulas. And the gauge transformations will be also A1 will operator of order 1, A2 operator of order 2. So, but these things, if you make this balance of order of operators, do not form DG algebra. Yeah, so I cannot really formulate it from Markov equation in one DG algebra controlling the orders. And yeah, it's a bit kind of funny situation here. And why I want to control the orders? Because if I say I have differential operators, sheaf of differential operators of any order, and I have some kind of non-compact space, then in some domain it will be order 10, another domain order 20, it will be unbounded. Yes, it will be completely idiotic unboundedness, which the reason will go away. But anyhow, one can formulate such things. And now I explained when truncate starting from degree 1, also degree 1, also degree 0. But if you don't truncate, just suppose truncate to degree -1, because here my sheaf starts, I get 2 groupoid. So it's a bit more complicated notions, and so it will be sheaves of algebroids. It's not a sheaf of algebra, but algebroids. It's kind of it's a name which I coined for exactly for the situation. Like group voids are a little generalization of group, and we get symmetries of symmetries. And algebroids is a similar story. So it's a sheaf of categories which are locally equivalent to sheaves of pre-rank 1 modules or some subproducts. So it means that roughly that your algebras only up to inner automorphism. So there will be some extra cycle on triple intersections. You get what really here goes on. You get on each small open domain you get star product. On intersection you get gauge equivalence. But on triple intersection, positional gauge equivalence will be not identity. It will be a joint action of 1 plus some high terms invertible element in my algebra. And this invertible element satisfies some cycle condition on quadruple intersections. So it's a little bit more complicated notion. So there's a sheaf of algebroids, but over this category, you consider again left modules, and you get still well-defined sheaf of categories. And you get deformation of sheaf of categories, and also you get deformation of global category. What's in the global category? You can have very few objects. So the category can guide after this deformation. And what is the core of formality theorem? If you have Poisson manifold, complex Poisson manifold, so we get manifold by vector field. 65 is now connotation in polyvector field algebra, so it's commutated with self-zero, so it's Poisson structure. Because we have this, it's particular class of so we get such guy, and then we get canonical sheaf of algebroids and have canonical deformation of complexes and sheaf of categories of perfect complexes. And explanation is very obvious because in this polyvector fields we have no differential. And so we have extra GM symmetry, and if you have Poisson structure, you can consider one prime per family of Poisson structure multiplied by parameter, which start from 0. And this is passed in a more catastrophic system from algebra T poly, and hence this and hence T0, T dot poly, and then for quasi-isomorphism you get something in poly differential operations. Already here this is something pretty complicated. It goes on. It's unavoidable to use algebroids. Why we should go to this beginning of this algebras? You have this sheaves when it truncates to degree 0. When it truncates to degree 0, we remove this sheaf off from the beginning. We still get quasi-isomorphic complexes of sheaves, but they're not quasi-isomorphic complexes with DG algebra. So one should really go to this this German part unavoidably, and so we cannot say that we have a sheaf of products, algebras. Also, naively it could be that we have a sheaf of algebras. And the situation is pretty complicated here. There was it was analyzed by Maxim Kontsevich many years ago. Probably we have the following question. Imagine we have complex symplectic manifold, maybe compact one, like case surface. Or there's not so many examples, but one can imagine that we work with some complex symplectic, homomorphic symplectic manifold. And then when consider deformations local model space deformation, you get you describe the classes in second homology of your variety. And this is a locus where you have actual sheaf of algebras. And this locus is kind of tricky. It's not, you cannot say what is it. It's looking on polyvector fields, you get a naive approximation to this locus, but it's wrong. So when you get actual sheaf of algebras, it's different from this guy by Razan-Witten invariance of your symplectic manifold. So some kind of finite important polynomial dependence, non-trivial dependence parameters. Okay. Yeah, so I started to speak about symplectic manifolds. So let's do it more seriously. So if Poisson structure comes from symplectic structure, so we have non-generic form, close to form, taking into the Poisson structure, then any star product. If you consider star product, you say that it's compatible with the symplectic structure if anti-synchronization V1 GF, if it's an anti-synchronization of first term, it will be automatically bi-vector field, Poisson bi-vector field, and you say that it's exactly your inverse to symplectic form, and yeah, you consider any star product from which you know the first term, and then locally after some Gauge equivalent, it's actually equivalent to standard Maillard product. So that's a formula in local coordinates. It's not the same formula which Anders wrote yesterday, because here it kind of bit not symmetrized form of V1. Okay. Actually, this formula has a following meaning. You think about variable y, it's hbar due with the xi. Yeah, and you write kind of like x on the left, due with x on the right. Yeah, that's how we multiply differential operators. Yeah, but globally, the isomorphism class of sheaf of algebroid. Okay, I just had this night to check what I wrote. No, it's actually next. I should parse this sentence, yeah. Because it's sheafs of algebroid which are locally given by the star products, but you consider global guys, and they're determined by the leading philosophy class, isomorphism class. It just Laurent series in hbar with coefficient second homology, second full term is this class of symplectic form. Yeah, in particular, if your variety has 0 H2 homology, there's no invariance whatsoever. All things are like it will be a fine space, it's the kind of non-trivial products, but this daily philosophy class will be 0. Yeah, and the canonical quantization, which I mentioned, associated to Poisson structure, for the symplectic case, corresponds to the straight formal path. We just consider only one term, because we can like multiply Poisson structure by hbar, or we divide symplectic structure by hbar. And it will be some important small result, which we'll use later. It's quantization of Poisson divisors. In fact, in this form of quantization, main picture will be that if you have some Poisson submanifold that correspond to quotient algebra, it's definitely not the case. There are examples which I think Thomas Hillebacher produced. First example, some Poisson structure in dimension maybe 5 variables, and you get point where Poisson structure vanishes. So you get like Poisson submanifold, one symplectic leaf is a point. You get this Poisson manifold point. Namely, you see that the quotient algebra, you should get one-dimensional presentation. Algebra doesn't have one-dimensional presentations. Yeah. So it's named features that Poisson symplectic leaves correspond to quotients. It does work, but it works for divisors. If you have any divisor, yeah, it's Poisson. If it's ideal sheaf, it's sheaf of Poisson ideals. It's this definition, but it's actually a pretty geometric notion. For case of divisors, it doesn't depend on choices of reduced or reduced or reduced. You consider reduced divisor, and after you throw away something of codimension 2, you forget about the importance. You consider locus of smooth points. And the slope of false points should be close Poisson happy terms. Yeah, it's very easy to check that. Should they will automatically any multiple will also Poisson device. Yeah, yeah. So it's you take kind of this Poisson divisor, and example of such things is the following. Suppose you have a open in your Poisson manifold, you have open everywhere dense symplectic leaf. It will be a common situation the rest of my talk. Then if you consider Poisson structure raised to, so it means that this guy has even dimension. Consider top degree of Poisson structure, get section of anti-canonical bundle, and it's not vanishing to generic point, and vanishes at some divisor, maybe some multiplicity. So you get, so it's example how you get naturally Poisson divisor, and it's associated with the complement of this open leaf. And the claim is the following. In such situation, when you have canonical quantization, not arbitrary quantization side of Poisson structure, but canonical one, then it will have canonical, the sheaf function contains a canonical two-sided ideal. This notion of ideal invariant under inner conjugation, so it's okay. And which will be flat deformation of the divisor, of ideal in the classical limit. And because we are smooth manifold, this Cartier device is Cartier divisor, so I can write as zero locus of some function. So I choose any function, German function at any point, which vanishes exactly at my divisor with right multiplicity. Then take, I think, I'm not totally sure. If you take any lift of this guy, then you get a generator of ideal pre-run model, but in fact it will be two-sided ideal. It will be automatically not left ideal, it will be automatically right ideal. It will be two-sided ideal and get quotient algebroids supported on divisor, deforming sheaf of functions on maybe non-reduced divisor. And what is the definition of this sheaf of ideals? And again, let's do it smooth points of reduced divisor. All formals works in coordinates. So I choose good coordinates near point such a divisor given by some power of first coordinate. Is power of the first coordinate. The conditions this divisor is Poisson means that by vector field it belongs to kind of it's logarithmic along the divisor, which in plain terms means that it's linear combinations of by vector fields x1 derivative x1 and derivative xi. I just look for derivatives in coordinates with indices bigger than 1. And now you look on explicit formals for deformation quantization and coordinates, how you do star product. And then you see that if you consider x1 to power k times this function, it's canonical star product in affine coordinates, it will be two-sided ideal. And x1 to power k will be its generator. Both as a left-right module, right module, bimodule, whatever. Yeah. Yeah, and then one can extend the whole divisor by Hartog's principles. Yeah. Okay. Yeah. Yeah. So it's maybe the only kind of proof of some result. Okay. Yeah.
Are you assuming that the divisor is multiplicity 1 because the
No.
Poisson is generated by x1 dx1 wedge dx?
No. I can see that it's the condition of being Poisson doesn't depend on multiplicity. Divisor.
But what if gamma is x1 squared dx1 wedge dx2?
Sorry. Me. Yeah. Yeah. Okay. Maybe let's say it will be multiplicity 1. Yeah. Maybe you're correct. Thank you. Okay. Yeah. Let's say multiplicity 1. And, yeah. It really doesn't matter. Okay. Yeah. So now it will be little diversions. It's not really my point of my interest, but something which is interested after I prove the differential quantization, how to quantize algebraic varieties. Here are plenty of examples like character varieties, which the subject of yesterday talk banners. But kind of what is general philosophy? If you want to do something with algebraic varieties from point of view of analytic topology, it's better to use varieties to be compact than I can apply the other principles. So coherent sheaves in one sense and the coherent sheaves in another sense. And let's start with the compact algebraic Poisson variety. And when we write this analytically, this gadgets, this solution of Markov equation, we deform. We'll have certain global category, and sometimes it's still algebraic, so it will die completely. And by algebraic, I mean it will have a generator, which will be deformation of a generator of a category in algebraic case. It's not always the case, yeah. So one can hope that it will be. Always, because for example, if you have a variety, you can imagine situation can variety is just with zero Poisson structure, but you can deform to non-algebraic ones again, like case with algebraic torus. So even result is H0 of H2 and H2 of 4, you can deform to non-algebraic one, so it should be kind of like. But in many cases, when variety, kind of rational variety, or have maybe the right condition H1 of this sheaf 4 and H2, this sheaf 4 when tickets will be sufficient in this case, then you always have a deformation with algebraic, and it's not kind of wrong order. The first example should be the following. It's the second example. Namely, you can see the compact algebraic variety. Take compactification of cotangent bundle, so it will be productization of T star plus 4 of hbar to compactify the cotangent bundle by projective space. It will symplectic structure cotangent bundle will give Poisson structure. It extends Poisson structure with this guy. Now, so this will be a perfect example of such compact algebraic Poisson variety. And when you quantize it, you get completely a category, which is nice category, saturated category in the sense of derived algebraic geometry. You can do things for non-compact algebraic variety. You compactify by dividing this normal crossing and consider logarithmic cotangent bundle with reducing construction. So cotangent bundle smooth manifolds can be compactified by something nice, and the deformed category is also nice. Then there is a multiplicative case. You consider torus, even dimensional torus, say, actually we're not necessarily I write symplectic one by analogy with this examples, but you can actually take torus of arbitrary dimension and Poisson structure, which is constant in logarithmic coordinates. Symplectic case it could be, for example, this standard coordinate torus. You take any toric compactification, not necessarily the projective one. It will be automatically Poisson variety, and it will be again find objects for deformed categories. And kind of third example is elliptic case, where you get symplectic leaves are related somehow to elliptic curves, and there's a great class of example taken an SK output, which can make kind of homogeneous affine spaces, can project spaces on general, you can make Poisson structures on projective spaces, which are given by some kind of quadratic brackets, and the whole thing, at least for this cases, one can show that you get nice category sample deformation. If you do non-compact algebraic Poisson variety, how to quantize it? It's possible strategy that it's definitely not optimal one is to choose an algebraic Poisson compactification. Such a complement is Poisson divided. So that's why I explained the story about Poisson dividers. What happens if we are lucky and for the compactification the deformed category is still algebraic, we can declare what is the deformation of category perfect complexes over the series in hbar. It should be localization of this global category for the quantification by the full subcategories of the system of objects supported on the complement. And to consider perfect complexes, so I think it will be really nice definition. And if you do like affine space, the standard symplectic structure, you can quantify it in many ways, like produced by big projective space or is potential bundled by long potential space. There are many quantifications, but whatever you do, you get category of perfect complexes of by algebra. Then you can see the hbar differential operators with coefficients, so like finite linear combination of x and hbar with x with coefficients in formal series in hbar. And the category of perfect complexes is very nice. It's again algebra finite type. Like this, and this has a similar picture in the multiplicative case. You have invertible variables x, and instead of derivatives, there's few different derivatives that use exponent of hbar as a form of our series. But now you can see that if hbar is, you replace hbar by some concrete number, no, like 60. Okay, you get a very concrete number exponent of this number, and you get countably generated algebra, and the same thing works in elliptic situation as well. Because you get elliptic functions, you get universal cover of elliptic curve C. So a priori, it behaves as a form of our series, and that looks like a germ, but really it's actually an entire function in hbar. And that led me a long time ago to ideas that it thinks maybe exists non-perturbative, because essentially all examples have these three forms. Rational trigonometric elliptic, just a little bit more like case-free direction, but it also has some kind of Taylor's theorem and again entire function. So that leads me to the conjecture which I just want to present here. That it has any complex Poisson manifold. I forget about now algebraically completely because it's not really relevant. Manifold of scalar type. So scalar type means that it has scalar metric. And then we should have a canonical category, global category of what I would call perfect complexes of sort of non-perturbative quantization of this variety. So it's no small parameter, and enriched our curve suit means that combs are finite dimensional spaces. And with a bounded T structure. So because we have before limit we get or in the form of our series we get like complex shifts of algebroids and we get shift of models, not necessarily.
Is this conjecture for the canonical quantization or anything?
No, it will be canonical quantization, It will be canonical quantization, So instead of form of our series, we can really put arbitrary value of hbar. And such that if you consider, so now it will be some murky reverse dependence on your manifold and Poisson structure should be analytic. What does it mean? You get for each value of parameter, you get a category. What does it mean? Depends on parameters. It's analytic. Yeah, I should do kind of measure some kind of analytic sets of finite type or DG manifolds, maybe supermanifolds with finitely many coordinates, and we deform a little bit homological vector fields, and zeros can appear, disappear. So the question to say what is a family of categories even for without quantization? You have family of family of complex varieties. Then for each value of parameter you get category of perfect complexes, and it's clear that things can holomorphically depend on parameters, but things can jump at some rational points up and down. Yeah, so it's a pretty valid situation for actual categories. There was a story of what's called condensed something, yeah, by Scholz and Clausen, functional analysis, and what here goes on for compact non-algebraic complex manifolds, one can define some big categories, some realizable categories, using some appropriate notion of nuclear spaces. So since there's some big category which doesn't have compact generics, so then consider compact properties will be perfect complexes. And this category described in some terms of some very concrete terms, some couple of DG algebras, big infinite dimensional DG algebras, but here one can formulate notion of analytic dependence directly for this big category. I have no idea for what things I'm talking. Is there any big category behind? This definitely should be perfect complexes, but can disappear if ordinary values of parameters. It's a bit tricky thing. As an observable structure, what we have here, if we have, one can try to formulate various properties, expected properties, looking on homomorphic family of non-algebraic varieties. For example, if you have any analytic family of the base, we should get direct image, get sheaf of categories on the base, enrich over the sheaf of categories of perfect complexes. So it will be like forms of the finite dimension complexes depending on the base. But it's not exactly, because if you consider fiber of this and try to localize this point, it's not clear that you get the category which you have at a given point. Yes, even without quantization, it does seem to be sufficient notion. Okay. So it's a nice conjecture, but you see that there's something wrong. There are something wrong with parameters. They're missing parameters. You start with usual method with zero Poisson structure, and in this situation, in my conjecture, is a formulation. This mismatch of just on the level of tangent space. On the level of tangent space, you deform Poisson manifolds over dual numbers. The tangent space will be direct sum of two pieces. First, homogeneous coefficients and vector fields, deformation of your manifold, and H0 of H2 to the deformation of your Poisson structure, which is initially zero. And for when consider polydifferential operators, quasi-isomorphic polyvector fields, you get also extra term H2 of extra coefficient H4, which respond to these jobs. Two jobs. And it's a proposal how to cure the situation to get really one-to-one correspondence. And the proposal, this is something strange proposal. I proposed to start with the following things. Which, first of all, if you have your manifold with zero Poisson structure, you choose a U1 job. So U1 will be numbers, complex numbers set to value 1. And you consider like two cycle of this coefficient in the group U1. So if you have this U1 germ, then at least you a sheaf of algebroids. You consider trivial sheaf of algebroids, and then on triple intersections, we consider this composition of isomorphism of the conjugation by constant, which is this term for this cycle. And because constants, they don't really enter in any formals in deformation quantization. They sit in the center. And because of this, one can write deformation quantization formula for this twisted by constant parts as well. There's really no trouble. And then after that, you at least in formal series, you have canonical deformation quantization. So we can first twist by constants, then do canonical quantization. We get some parameterization. Okay, guys? Yeah. You will ask why choose constant only actual value equal to 1. I can use C star, but it seems it will not work for C star globally. So we edit this, we'll see it later. So edit U1 twist, we restore missing parameters, but then kind of make too much. Okay, now too many parameters. For too little parameters, not too many parameters. Because what is going on, I replace my sheaf of, let's say, TGL algebra by what? In degree -1, I put constant sheaf, I purely imaginary numbers, turn to 1. But in degree 0, take vector fields, by vector fields, like usual, so I get this bit different sheaf of DGL algebra. It will have just center, not a hierarchy, it all with the rest, it will be really direct sum. Now this condition for being Keller, which wasn't really justified, it start to play some role. For Keller varieties of Keller trap, consider H2 with coefficients in imaginary numbers, which maps to H2 with coefficients is 4, which the thing which will add in deform category, it will be epimorphism. So now we have more parameters as needed. And the epimorphism has external real Keller classes. Now we have a different problem. Before we have not enough parameters, now we have too many parameters. But it's not really trouble. Because we have this epimorphism, one can produce some pretty interesting formula in this situation, but I don't have time to do it. The story is the following. You have this consider two sheaves of DGL algebra. One will be IR, T, H2, T, and so on. Another will O, T, H2, T, and so on. And you get epimorphism on the level of sample space. And I claim you get epimorphism on the level of Maro-Cartan, solution of Maro-Cartan equation as well. And it's something you should calculate using polyvector fields. It's some property of this two DGL algebra. You get epimorphism on just homology of our gamma, and it's pretty tricky formulas. So you get some equivalence relation, which is not formal one. It's polyvector field with actual germ, analytic germ from the space of solutions, and what here goes on is the following. Maybe just one simple remark. When I consider both polyvector fields and or differential operators, polydifferential operators, this two sheaf of DGL algebra contains a central subsheaf constants, not imaginary but complex constants in degree -1. And because it's central, it means that you can twist any solution by any locally by class of H2 with complex coefficients. So the abelian algebra H2 homology with complex coefficients acts on this modular space, and actions a bit tricky. And for example, for this tensor, when I get this guy, it maps with IR, it maps to homology of full polyvector fields. And there's the action of H2 or this complex coefficients. One can write explicit formulas, and then this identification comes from some kind of part of Gaussian transformation.
This is, the thing to deal with the algebra, the heuristic of homology algebra, plus the connection.
Yeah.
Isn't this foliation of parts just the argument of information?
No. No, already here it's kind of pretty tricky. Because there's no prism here, but I didn't put it on my slides. Yeah, one can have kind of very thick. Yeah. This one can replace. Sorry, maybe to write how to handle this redundancy of parameters, it's already not trivial, but it's really a great geometry because you need from the polyvector field language. Okay. Yeah. Okay. So, what is the evidence for this very optimistic conjecture? Yeah, of course, there's concrete examples when you have explained that trigonometric quantization, electric, rational, so on. But I want to forget about algebraic geometry, so to do kind of really non-algebraic examples. And so essentially, the only example which I have is the case of flat torus, complex torus. We consider varieties which is Cn divided by rank to n lattice, and homomorphic structure is because number space is trivial, bundles trivial, translationally invariant holomorphic bivector field, and now we get this U1 torsor, yeah, we get this parameters, then moved out by this relation which I explained, and then I get something which is covering of some really nice stack. Namely, you consider the following domain. You consider lattice of signature to n, this usual split by linear form. Signature to n, complexify it, you get complex vector space of dimension 4n is bilinear form. Now consider isotropic Grassmannian subspace of middle dimension isotropic, and take open part of this guys which intersect trivially around or complementary to the complete conjugate. It's some kind of code structure, and you're moved out by a symmetry group O to n, and I get some stack. The portion is very, very non-causal. The group action is equivalence orbits. And that's what's come from this this picture. And again, many years ago, I can actually talk on this symmetry portions of 10 years ago, something like this. Yeah, I conjecture that this stack parameterized analytically kind of categories which is kind of non-algebraic quantized story with jobs. But it was at that time came from different perspective in A model. Consider real torus of real dimension to n with translation invariant symplectic structure. It should have some Foucault category, and then we add B field, you can job with U1 job, and here there's no redundancy. In this cases, you get actually real imaginary parameters, and you get some class of categories. And if you look on the code structures of the periodic cyclic homology, you get an idea should divide by this group. Yeah, for example, we take two-dimensional torus, you get symplectic structure, you describe the thing by complex number q with absolute value less than 1. So we exponent minus area symplectic form, and B field will be imaginary part. But this is covering of modular curve. And the categories depends on the class of elliptic curve, which you cannot see from symplectic geometry. And here we get kind of natural modular spaces. And again, from this B model, you can put this U1 torso, U1 U1 job. Sorry, if you consider U1 job, I get the same parameter space, the same condition, to the same condition. And if I allow C star drop, which namely look like a sheaf of categories, look the object exists, it completely breaks down. It breaks down this transversality condition. Yeah. So I kind of really don't know what really goes on. Should I allow break this condition, or but is this U1 is compatible with mirror symmetry? In general, C star also looks kind of okay. If I have C star drop, then I can have a well-defined notion of category. Maybe it will be, I don't know. Yeah. So that's about compact Poisson varieties. Yeah. If you do the whole sequence works, it will really be very convenient way to encode categories. It's kind of like generalized orbit method. We said it's compact Poisson variety, and maybe a little bit U1 drop, maybe a little bit redundancy, is geometric description of categories that we can kind of say communication with this language. But now I'll talk about some other types of categories which are also very nice. And also have finitely many parameters. What are them? I consider symplectic manifolds, maybe now non-compact. And I want to say, define something like object with compact support on non-perturbative quantized symplectic manifold. Yeah, so suppose I have this non-compact guy, then how we should proceed? First, we should choose a Poisson compactification, even it's not algebraic one. And I think it's really close to very what's really essential in this situation. I don't want to have to quantize symplectic manifolds, which are like small Stein domains. I want to have really infinite volume, and this Poisson compactification is a way to say this. It's very large. So this Poisson compactification of hler type. So it's compared to this Poisson divisor. Then we expect from the whole picture that we get actual non-perturbative deformation of perfect complexes. One can also get this U1 drop. I just skip it for brevity. But also one can hope that this category perfect complexes on this divisor at infinity. It's also deformed not formally, but non-perturbative hbar, and you can deform not just two categories, but a functor. Non-perturbatively. And then we can declare what is the category of object with compact support, imitating things which you have in classical limit or formally close to classical limit, kernel of this functor. Restriction is 0. And the function will be finite dimensional, because the function will be finite dimensional over C. But it's a different story, so it's not quantization of compact variety, but compactly supported object of some variety. Yeah. And then if you go do things over form power series, then the resulting category depends on this delimited also class. And the conjecture is this category, if you deform it with all parameters, depends on the parameter only through this homology class. Now, what I want to say is that, if you have a family of complex symplectic manifolds, which included is a family with some compactification, and let's say topology of the open symplectic leaf doesn't jump, maybe complement things smoothly, but the whole open part doesn't jump. And if a class is covariantly constant, then the categories should categorize from a local system. And this is kind of generalized non-linear Penderecki connection, I was called this thing. So what is an example of this story? We take a tangent bundle to complex manifold. Yeah, we can compactify simply using productization of infinity, so we get a well-defined notion, and then it's natural to expect this whatever this guy will be category kind of D modules with zero singular support, or zero section zero support, or it has card which is a category bundle to the flat connection. And then by usual Riemann correspondence, this category is the same as finite dimensional representations of fundamental group, and it's locally constant if you deform the variety. And now that's an example. You can change complex structure in a variety without changing topology, and then as analytic categories, these guys do not change. That's an example of Penderecki connection. And if, for example, my variety algebraids, and I get algebraic modular spaces, and which I identified as analytic varieties by transcendental methods. Yeah, this story talks about for just the connections of one can go one do certain tweaking all holonomic modules. Namely, what you should do, you have you consider Poisson simplification of cotangent bundle. Now start to make some blow-ups, which still preserve keep the variety to be Poisson. It's very restricted amount of blow-ups you can do, but it seems at least in dimensional wise one is easy to analyze and it's plausible in high dimensions that one can make blow-ups in such a way that open symplectic leaves will increase. It will be cotangent bundle, but you add some exceptional divisor to it, so it will have now non-trivial class of symplectic form. Before it was 0 plus, and again after some tweaking, this following the modules we can promote to object with compact support on appropriate blocks, and we'll cover even here vertical correspondence for all following the module. Yeah. So why this thing depends on homology class. And that's kind of corollary from another story, which is called generalized Riemann hybrid correspondence, which proposed with Jan several years ago. We said that again some kind of Foucault category of Y, where you have a really interesting B field of X will be equal to this complex support Foucault category will be equivalent to this perfect category is going to support for quantization. And Foucault category by its nature depends on the class. Yeah, so that's the reason for this picture. Yeah, I think I'm at the end of my slides. I want to say that the categories of the second type, which I started to introduce to this complex symplectic manifold with good simplification, they have their own modulus text, which again kind of in examples is some kind of like host structures, like for the case of Tori, you get some complex Lie group, some subgroup, sometimes non-reductive, and divided by some arithmetic group, and it will be non-Hausdorff, many interesting non-Hausdorff stacks covering various examples. Yeah, for example, for in the elliptic case, we get some SSVZ symmetry, which was discovered by Varchnik and Felder. For elliptic equations, you get some essence with it. We define various categories. Okay, thank you.